Kia ora. Here's a Molview app that is brilliant also for looking at spectroscopy. So just go to molview.org and download it if you haven't already downloaded it. This is a sort of the landing page. Just click on close. Caffeine is the default molecule, so just consign that to the bin. Now, if you wanted to investigate spectroscopy, you can draw your molecule using these elements. So if I wanted butane, for instance, I would just drag 4 carbons. I would then just simply click on this to add the hydrogens, 2D to 3D, and you would get something like this. And you could, although this doesn't show the carbon-13 NMR, hopefully you can see that those 2 molecules in the 2 atoms in the middle are in the same environment, and the 2 ones on the outside are in also the same environment, but different to the ones in the middle. Now, if you go to the tools, then you can go to spectroscopy, and you see it's loading spectra. Now we can choose between the mass and the IR. If we look at the IR spectrum, then you can quite clearly see all the CH stretches and the CC stretches and nothing else, because that's all what I have. If I look now at the mass spectrum, then you can clearly see that I have got a peak at 58, which is the molar mass of butane. Notice there's a tiny little peak there, which is the isotopic peak. This is 60 times bigger. And we have a peak at 43, which is normally the propyl fragment. And you'll have to be able to draw the fragments for this. So let's now look at some other examples. Here's butanol. So it's butane with an OH, and you can see how the O has withdrawn electron density away. So these are all in different carbon environments, and this carbon will be in quite a different environment to the others. And if I look at its IR, you can see that parabolic OH peak. Otherwise, others are similar. And here you can see we have something slightly different, and that's because the 74 is actually the M plus peak, and we know it's not 73 simply because that's not in a 1:60 ratio, which means that this peak at 73 is actually the M plus minus 1 peak. It's a loss of hydrogen, which has caused that peak at 73. Very common in carboxylic acids and alcohols. So here's an example of an isomer of the one we had. Okay, where these two are now in the same environment. And if I look now, we have that same parabolic peak. Don't worry about that. But otherwise, here's that CO peak very clearly. Otherwise, those are the CH stretches. And here's the mass. And now you see the M plus peak is quite strong. That's the M plus minus 1. And that tiny little peak there is that isotopic peak. Here are some other examples very quickly. Carboxylic acid. And again, you can see there's a strong withdrawal of electron density. These are in the same environment because this bond here can spin around. So although that looks slightly different to this side, it can spin, so they'll be equal. The one in the middle, though, definitely looks different, and so it will be in a different carbon environment. If I now go to its mass spec, you can see there's the peak at 88, as we'd expect, with a little bit of an M plus minus 1 and a slight isotopic peak there, and a strong peak at 43, which again is the propyl. You can work out this one, what you think that one is. And here is the infrared, and you can see that broad triangular. It's not parabolic at all now, it's broad triangular because of all the OH hydrogen bonding. You also see the carbonyl peak very clearly over here. Here's the mass spec, and you can see it should be 88. So, yep, I think it is. I haven't looked actually. Here is now another isomer, which is the strong triangular peak. And here's now an amine. And very, very quickly, if we look here, it's now definitely an odd number for the amine. And finally, there's that 2-prong for the NH2 group, as well as the CH stretches over here. So have fun building molecules and playing around with them and seeing what the spectra looks like. Kia ora.